In this video tutorial, we will create a tennis analysis system using OpenCV Python and YOLO. So here is a quick output demo. So you can see over here, we are detecting and tracking the players and the tennis ball. And you can also see we are also detecting the tennis court key points. For this, we will fine tune the Resonance 50 model on tennis court key points. Along with this, we will also apply a filtering mechanism to detect only the players in the field by selecting the player that are closest to the court key points. So there are a lot of things that you can learn in this tutorial. So let's get started with this. So I have just created a project in my PyCharm community edition over here by the name Tennis Analysis System in my local D directory. So first of all, I will just create a requirements.txt file. In the requirements.txt file, I will list all the packages that we want in this project. So we will be using YOLOv12 model as YOLOv12 comes under the Ultralytics package. So we will also be using the YOLOv5 model. So we will install the Ultralytics package over here. YOLOv5 and YOLOv12 both models are released by the Ultralytics. So and both comes under the Ultralytics package as well. So we own first with Ultralytics package, OpenCV Python package, and NumPy package, Matplotlib package, like many other packages also get installed with it as well. So we'll only install the Ultralytics package. In this tutorial, if later on we require some other package, we will also install along the way as well. So currently we only require the Ultralytics package. So to install the Ultralytics package, I will just write here in the terminal pip install -r requirements.txt. So when I just run this, so it will install all the packages that are listed in the requirements.txt file. Currently, we have listed only one package, which is Ultralytics in our requirements.txt file. So this will install the Ultralytics package. So you can see that Ultralytics package is being getting installed, and while the Ultralytics package gets installed, OpenCV Python, Cbond, Torch, SkyPy, TQDM, like many other packages are also installed along the way. Like you can see over here, like NetworkX, MPMath, SymPy, so Jinja2. Like you can see that number of packages are also getting installed along the way as we are installing the Ultralytics package. So I will also add some input videos over here, or I will just add one input video. So I will just create a directory over here. Input video. And inside this, I will add, we might add some more videos. So we can just rename this to input videos. So I have renamed it to input videos. So I will just add an input video inside it as well. And I will just add an image that is taken from the video. Okay. So let me add both of these. So if you just see over here, I have just added an input video of a tennis match. And here I have an image as well that is taken from the input video. So that looks good. Now, first we will see how we can detect and track the players using YOLOv12. So I will just create a .py file over here. By the name YOLOinference.py. So first of all, meanwhile the packages are getting installed, we can write some initial code over here. So first of all, we will import all the required libraries over here. So we'll write from Ultralytics import YOLO. Then we'll load the YOLO V12 model. We'll write model is equal to YOLO and we'll write YOLO 12. So YOLO 12 V12 comes with 5 different models: YOLO 12 Nano, YOLO 12 Small, YOLO 12 Medium, YOLO 12 Large, YOLO 12 Extra Large. Okay, so YOLO 12 Nano is the fastest, but it is least accurate, while YOLO V12 Extra Large is the most accurate, but it is less fast. Currently, I don't have a GPU in my local machine, so I will be using YOLO V12 Nano model. Okay. So next we just need to perform predictions. So first of all, we'll see how we can perform detection using YOLO V12 on this input video of a tennis match. So I will just write model.predict in the source. I will just pass the input video. So I will just write input videos and I will just write inside the input videos directory, we have input video.mp4. And we will just want to save the output video. So we write save is equal to true. Okay. So that is looking fine. So now you can see that the package installation is also done along the way. So we can just write over here, Python YOLO. Okay, this will take a few seconds. So currently it's indexing, so this will take a few more seconds. So we can just write Python YOLO inference dot py. And we can just run this up now. So soon the processing on the video will start. It will do the detection on each of the frame one by one. So this will take some time before it starts the processing on the input video. So now you can see that the processing on the input video has started. So first it has downloaded the YOLO 12 nano model weights. Okay, so now you can see that the complete video is being divided into 214 frames and it's doing detections on each of the frame one by one. So you can see that it's currently performing detection. So let's wait for this to finish, and here in the runs detect folder we will have our output video. So it will take some time to complete processing on all those 214 frames. So the processing on the input video is completed, and here you can see we have the output video in runs detect predict. So let me just show you the output video. Over here, if you just go to runs detect predict, so here you can see we have our output video. Let me just show you the output video first. So now you can see that we are able to detect the persons over here. But you can see that we are not able to detect a tennis ball. Like detection results for the tennis ball are zero. Like we are unable to detect a tennis ball. Okay, but we are able to detect the persons, but not the tennis ball. So like we want to detect the person as well as the tennis ball. So our aim is to detect the person as well as the tennis ball. So currently we are only able to detect the person. So let me just close this. So now if you want to implement tracking, so what you can do is you can just write results is equal to model dot track. Instead of predict, you will just use a track. And in the source, you can just pass the input videos directory, and there we have the input video.mp4 plus we will also save the output video. So we'll write save is equal to true, and I will just set persist it equal to true because we will have We just want to tell our model that there is a frame coming next. So therefore, we are just setting persist is equal to true. And what we do in object tracking, basically assign a unique ID to each of the detected objects. So this is what we do in object tracking. So we are using Ultralytics for object tracking. And in object tracking, okay, so there is an error. Okay, so I just need to fix this. Let me just run this again. Might work. Okay. So we just need to install the lab. So let me just do this. To solve this error, you can just go to the terminal from here and you can just write pip install lab. So you just need to install the lab package. So okay, so and here we can just write. We also require the lab package to make this project run successfully. And now I will just write Python YOLO inference.py. So we are just running this script.py script, and let's see if we are able to implement object tracking as well. So let's see if we are able to integrate object tracking with our object detection model. So now you can see that the complete video is being divided into 214 frames, and it's doing detection on each of the frame one by one, and then it will also integrate object tracking. So in object tracking, what we do is we basically assign a unique ID to each of the detected object, and that unique ID is assigned to that object until that object remains in the frame. Okay, so that object will retain that unique ID until that object is within the video frame. Okay. So this is all object tracking. In object tracking, a unique ID is being assigned to each detected object, and that ID will be retained by that object until that object is in the video frames. So currently it's currently processing the input video, and the input video is being divided into 214 frames. And detection on each of the frame is being done one by one, and after detection, we implement object tracking. So let's wait for this processing to get finished, and then we'll go ahead. So the processing on the input video is being completed and our output is saving runs detect track 2. So inside this we have our output video. So let's look at this. Okay. So in runs detect track 2 we have our output video. So let me just play this output video and see if we are able to implement object tracking or not. So now you can see that each of the person is being assigned a unique ID. Like ID1 is assigned to this person, ID3 is assigned to this person, ID22 is being assigned to this person, ID5 is being assigned to this person, and ID2 is being assigned to this person. So each of the person is being assigned a unique ID. Okay, so that works. So now what we'll go ahead and I will just create a new directory over here by the name utils. And inside this directory, I will just create another .py file by the name video-utils.py. Okay. So inside this .py file, I will just create two functions. One is the read video function, and another is the save video function. Okay. So we will use OpenCV Python to read the input videos frame by frame, and we will also use OpenCV Python to save the output video. Okay. So first, let's create the read video function. So the input to this function will be the video path, and we can just write cap is equal to cv2 dot video captured, and we will just pass the video path over here, and we'll just append all the frames to this list, and we'll just loop through each of the frame one by one. So we'll just write true, and we'll just read frame. Just so if we are able to read the frame, then we'll append the frames into the list which we have created. So we can just rename to this list of frames dot append else if we are unable to read the frame, the loop will break. And we can just write cap.release. We are just releasing the video capture function, and this will return me the frames. Along with this, we can also create a save video function over here. The input to this function will be the output video frames over here, and the input to this function will be the output video path. Okay, so we will let me just create a directory by the name output videos, and we will be saving our output videos into this directory output videos. Okay, so we can just simply write for cc. We can just write cv2.video writer dash for cc, and we want to save our output video in the format AVI. So we'll just write mjpg, and we can write out is equal to cv2.video writer, and in the here we will pass the output video path over here, and here we'll have the for cc. We just want to process 24 frames each second, and here we just add the output video width and the height, like, so we'll just write output video frames 0. So this will contain the height. So the first parameter we'll pass over here is the height. We just calculating the output video like only calculating the first frame width and the height, and just passing over here. And then we'll just write for frame in output video frames. We just write out dot write frame. Okay, and we'll just write out dot release. Okay, so we have created two functions. One is the read video and other is the save video function. Okay, so that looks good. Next we can do is, so now we will just create a main.py file over here. Okay, so we'll just leave it currently as it is, and we will just create a new directory over here by the name trackers. And we will just create a .py file inside it by the name player tracker. So now we'll just write the code implement to track and detect and track the players. So now inside the player tracker.py, we'll write the code to detect and track each player in the field. So let's get started with this. So here you can see that we have utils.py. We have in the video utils, we have created two functions, read video and save video function. So if you want to access this function outside this directory, so we'll just write in it.py, right from dot video dash utils import read video, save video. So now we'll be able to access these two functions outside this utils directory as well. Okay. So in the step number one, we'll import all the required libraries over here. So I will just write import cv2, import pickle, then we'll write from ultralytics, import YOLO, and from in the side from utils, import no, uh, I think we don't require the read and save video function over here. So we can go ahead. So now we can just write class player tracker. So we can create a class by the name player tracker, and we'll just write init. Okay, so here we'll just pass the model path over here. Okay, so we'll just write self.model is equal to YOLO and here we'll just pass the model path. Okay, so now we'll just create two functions over here. First, we will create detect frame function. So now we want to detect and track each of the players. So we'll just write result is equal to self dot model dot track. Input will be the frame, and we just want to write persist is equal to true, just to tell our model that we are implementing object tracking and there will be a frame coming ahead as well. And we just can find the class names by writing results dot names. Okay, and we have just created an empty dictionary over here where we will just save the track IDs and the bounding box coordinates. So inside this dictionary, we will save the track IDs and the bounding box coordinates. In the key, we will have the track ID. In the value, we will have the bounding box coordinates. And we'll just write for box in results dot boxes. We'll just write track ID is equal to int box dot id dot list. Then we will also calculate the bounding box coordinates. So we can just write result is equal to box dot xy dot to list. Going ahead, we will also calculate the class ID. So we can just write box dot class dot to list. And we can then calculate the directed class names. So we can just write class name with, and here we'll just write class IDs. Okay. So we can just write if directed class names is equal to person, then player dictionary will contain the track ID and we'll also have our bounding box coordinates which are saved in a variable result. Okay, then this function will return us the player dictionary. Okay, so here we are only performing detection on a single frame. So in this function, the detection are being performed on a single frame. Okay, so if we want to perform detections on all the frames, so then we will just create a function by the name detect frames, and we will just write frames. Okay, we can just write here player detection. So we can just create an empty list over here. So in the player detections, we will append this dictionary for all the frames. Okay, uh, so we can just write for frame in frames. Okay, and just write player equal to self dot detect frame. So we'll call the above function over here, and the input to this function will be the frame. Okay, and we'll just write player detection dot append and we will append the player dictionary. Okay, and this function will return the player detections. Okay, so that looks quite promising. So now we will draw the bounding box coordinates. Okay, so we can just write define draw. Now we are just drawing the bounding box coordinates. So we can just write the input will be the video frames and the player detections. Okay, so we can just write output video frames. It should be an empty list over here. And we write for frame, comma, player dictionary in zip video frames. And we will also pass player detections over here as input. And as I told you that inside the player dictionary, we have the track ID and the bounding box coordinates. So we can just write for track ID forward box in player dot items. So we have x1, y1, x2, y2 bounding box coordinates, and we'll just write cv2 dot put text, and here we have the frame as well as the player ID. The player ID will be the track ID, and we have int x1, int y1, and we will just use simplex font, and the font scale will be 0.9. The color of the text will be blue, and thickness of the text will be 2. And we will also draw a rectangle around each person. So the input will be the frame. Then we have int x1, int y1, x int y2, and the color of the bounding box will be blue as well. And the thickness of the bounding box will be 2. And then we will just write output video frames dot append frame. Okay, and then we'll just return output video frames. Okay, so now we have written the code to perform detection and tracking on the players in the field. Okay, so now we can just go to the main.py file we have, and to assess this outside this to assess this class player tracker and all these functions we have here outside this directory, we can just create .py file, and here we'll just write from dot player tracker import. Okay. So we can just go to the main.py file now. So we can just write from utils import read video, save video, and from trackers import player tracker. Okay, so we can just write the main. So the first thing is to read the input video. Okay, so we can just write input video path, which is input videos, and we have input video dot mp4, and we just write video frames, and we have also created a function read video. Inside utils we have created a function read video which returns the frames. Okay, so we can just write input video path over here. Okay, so now we will detect layers. So we just write layer tracker equal to layer tracker. Now we just pass the model path over here, which is YOLOv12 Okay, so now we'll just perform detection and tracking on the player. So we can just write player detection is equal to player tracker dot detect frames. I think we should use detect frames function over here, and we'll just pass the video frames as the input, and this is what we only require. So detect frame functions only takes uh, video frames as the input. Okay. So next, we can just write draw output. We can just write draw output. So we just need to draw bounding boxes around the player. So we can just write draw player bounding boxes. So we can just write over here uh, output video frames is equal to player tracker dot draw bounding boxes. The input will be the video frames and plus we will also pass player detections. Okay, so let me just check. So yes, I'm right. Then you also want to save the output video, so we can just write call the save video function. Here we have pass output video frames, and here we have output videos directory, and inside this we will have our output video saved by the name output.avi, and then I will just write if then we'll just call this main function. Okay, so now we'll just run this main.py file, see if we are able to implement detection and tracking on the players or not. So now you can see that 5 persons, 5 persons. So we are able to detect the players. So the processing on the video will take some time. So I will just pause the video, and as the processing complete, I will be back. Now you can see that the processing has been completed on our input video. So you can see that here is our output video. And let me just see how our output video looks like. So we can just go over here and we can go to the output videos directory. And here we have the output video. Let me just play this up now. So now you can see that we are able to detect the player and we are able to assign a unique ID to each of the player, like an ID2 is assigned to this player, ID4 is being assigned to this player, ID22 is being assigned to this player, ID5 is being assigned to this player, and ID3 is being assigned to this player. So we are able to successfully implement player detection and tracking. So we have completed the first step. Okay, now, before we go ahead and implement ball detection and tracking as well, one thing you might have noticed that as we don't have a GPU in my local machine, so it take quite some time to process each of the frame one by one. So there is a solution. So we can save the output of these frames in a pickle format. So whenever we run this video and perform the same operation, it will not take the processing. So it will not take the processing time. So let me show you how this works. So we can just save the output of this frame in a pickle format. And whenever you run this video and want to perform the same function, so you will don't have to go wait for the processing. So you will have your output video ready at the same instant and you don't have to go through the processing phase again. Okay, so we can just go to the tracker and just open the player tracker.py file over here. And we'll just update this detect frame functions over here, detect frames function. So we can just write read from stub is equal to false. And we can just write stub path is null. Okay, so what we can do here is we can just create another directory where we'll save our pickle files. We can just write name it as tracker stubs. So stub path is none, so we can just write if read from stub and stub path is not none. Okay, then we'll just write with uh, with open We'll just pass the stub path over here and we'll read it as F, and we will just write player detection. We'll load the pickle file. Okay. But before we load the pickle file, we need to make sure that we have saved our detections in the pickle format. Okay. Or we have saved our output frames in the pickle format. So we can write if stub path is not none. Okay. And we can just write with open stub path. So we'll just save frames in the pickle format, and we can just write pickle dot dump, and we'll just pass the player detections f, and this will return me the player. We don't need to write this, we have already done this. So we are just saving our output video frames in the pickle format over here. So that looks quite good. No issues with this for now. Okay, so now we'll just go to the main.py file over here. Okay, and here we can just write over here stub path is equal to tracker stubs, and here we'll just write layer detections dot pickle. Okay, so let's run this. So now we will save our output video frames in a pickle format. We can just write detect and track layers over here. So now the processing on the input video will start. Okay, so now you can see that the processing on the input video has started. So let's wait for the processing to get finished and see if our output video frames are saved in a pickle format or not. So now you can see that the processing on the input video has been done. And if I just check that track stubs directory, now you can see that we have saved the output video frames in a pickle format. So that's look quite impressive. So we have saved the output of these frames in a pickle format. So now we can just start right over here. So we can just set this read from stub is equal to true. So we can just write read from stub is equal to true. And let me show you how this works. So now when I run this main.py file, this will take the output of, it will take the output of the frames from this pickle file, and we don't have to wait for the processing on this input video to get finished. So now you can see that I've just run this. So now you can see that we don't have to wait for the process and wait for the processing on the input video to get finished. And you can see that we have done. And if I just now open this folder, so now you can see here we have the output video, and you can see that if I just go to properties, now you can see it's 5.8, and now you can see it's 5.18. So you can see that it's correctly modified as well. So I can just open this up over here. So now you can see that we are able to implement the player detection and tracking, and we using object tracking, we are able to assign a unique ID to each of the player. So that looks quite impressive. So now we'll go ahead and we will now detect and track the tennis ball as well. So let's get started with this as well.
For tennis ball, the detection results with the pre-trained YOLOv12 model are not very promising. So we have fine-tuned the YOLOv5 model on tennis ball dataset available on Roboflow. So we have fine-tuned the YOLOv5 model on this tennis ball dataset. So you can see that we have this dataset available on Roboflow. So you can see that here we have only one class, which is tennis ball. Like we are detecting the tennis ball over here. Okay. So like for this, we have around 578 images. And here you can see that we have 428 images in the training set, we have 100 images in the validation set, and we have around 50 images in the test set over here. Okay, and we are using the version 6, the latest version. So in order to export this dataset from Roboflow into Google Colab Notebook, we can click on download dataset from here, and we can just click on download dataset, and then we can just click on show download code, and you can just select the format as YOLOv5 because we have uh, fine-tuned the YOLOv5 model on this tennis ball dataset. Because with YOLOv5 model I am getting the best result, so therefore I have selected the YOLOv5 model. So I'm getting the best results with YOLOv5 model for only for this data set, like for the tennis ball detection. For tennis ball detection, I've also fine-tuned the YOLOv12 model, but with YOLOv5, I am getting the best mean average precision score for tennis ball detection. So here you can see we have the code. We can just copy this from here. And here you can see I have prepared a notebook where we are training the YOLOv5 model on the tennis ball dataset, which I've shown you. So first of all, we will install the Roboflow and Ultralytics package. Then you can just download the dataset from Roboflow by just adding this code over here. Okay. So after downloading the dataset, you can just move to the training files, test and validation directories into you can just change that path for the training, validation, and test directories so they can move to the path where they can, so that we can train the YOLOv5 model on the tennis ball dataset. Okay, then here we just check the location of the dataset, and here using a command line interface, we are training the YOLOv5 model for 100 epochs on this tennis ball dataset. So, and we are using YOLOv5 large model, and mod is equal to train, and we are training the YOLOv5 model on this a tennis ball dataset for 100 epochs, as you can see over here. So here you can see we have our training results over here. So like, okay, so after the training completes, the mean average precision score with IOU 0.5, we are getting is 0.645 or 64.5%, and mean average precision score when IOU varies from 0.5 to 0.95 is 0.266. That's score is very good. And so here you can see, and we can download the best model weights as well. So we will be using the best model weights. Okay, so this is the complete process flow how you can train on the YOLOv5 model on tennis ball dataset. Okay, so I can just add the dataset link over here as well. So you can just simply go over here and copy this link, and you can add this link over here as well. Okay, so this is how it works. Okay, so let's move towards the PyCharm notebook over here. Okay, so now I will just go over here and create a new .py file by the name balltracker.py. So I will just copy all the code from the playertracker.py file and add that code into the balltracker.py file. Now we'll just update this code over here. So we have results. Um, so instead of this, so as we know that we have only one class, which is the tennis ball. So we can just add here, we will have ball dictionary. Okay, so we will just so as there is only one tennis ball, so instead of applying tracking, we can just apply the predict function, and we can just assign that tennis ball ID of 1. Okay, so we can just set the confidence score to 0.15. Okay, so here you can see, let me just update this code update from here. and this will definitely return the ball dictionary. So we'll just write results is equal to box dot xy dot to list. Okay, and then we'll just write. So we will just assign an ID of 1 to the tennis ball. Okay, so this will be the tracking ID. So now we have a detect frame function. So here instead of player detection, we will have the ball detection. Okay, so we'll just write the ball detections. Okay, and here we will have, instead of player dictionary, we'll have the ball dictionary. So here we have ball dictionary, player detections. Okay, and here we have ball detections. Okay, and here this will return the ball detections. Okay, so that looks quite promising for now. Okay, now we have draw bounding boxes, and instead of player we can have ball detections. Okay, and we can just change the color to 255 to 55. Okay, so we can just changing the color from red to yellow. So the tennis ball will have a bounding box of yellow color, and we will have the ball ID over here. Okay, so that looks okay. So here we will have ball dictionary. Okay, so everything looks now good. So, so instead of this, we can also have ball tracker. So now our launch book quite good. So our code is ready for the use. So we can just now open the init file over here. Okay, and we can just write over here uh, dot ball tracker import ball tracker. That looks really good. So now we will just go to the main.py file over here. And in the main.py file, we can just write over here return ethics. Okay, so we can just write ball tracker is equal to, so we can also write, we also import ball tracker. We have the model path, which is, so we have this, so we have saved the best model weights over here. So we will go to the models directory, and here we have tennis ball model, best model weights. Okay, then we'll just go to ball detections. So we'll just write ball tracker dot detect. We'll use a detect frames function over here, and we'll just pass the video frames over here, and we can just pass the stub path first. Okay, so we'll just write tracker stubs, and we'll have ball detection. Okay. So we'll just save the output of these frames in a pickle format. So like we did for the player detection and tracking. So we are again saving the output of these frames in a pickle format. So we are just saving the bounding box coordinates and the track ID in a pickle format for a tennis ball. Okay. So whenever we run this script again on the save input video, we don't have to wait for the processing to get finished. So our processing time will be saved because of this. So now we will also drop tennis ball bounding boxes now over here. We'll just write draw tennis ball bounding boxes. Because output video frame is equal to ball tracker dot draw bounding boxes. We'll just pass output video frames over here, and we'll pass the ball detections over here as well. Okay. So now let's run this main.py file. So I will just write Python main.py. So now the processing on this input video will start very soon. So this will take some time, and let's see how it works. So the processing on the input video has started, and you can see that we are able to detect a 10 small, 10 small, 10 small. Okay. So now you can see that the 10 small is being detected. Okay. So the processing on the input video has started, and this will take quite some time. Okay. So let's wait for the processing on this input video to get finished, and then I will show you the output video. So the processing on the input video is completed, and over here you can see that we have the uh, oh, we have the bounding box coordinate saved in a pickle format as well. So we have saved the output of the frames in a pickle format as well. So now we can just see the output video as well. So let me just show you the output video first. We'll just here. So now I will just go to notebook and codes from here. And here we have a telesense system, and here we have the output videos. So let me just show you the output video now. And let's see if we are able to detect a tennis ball or not. So now you can see that we are able to detect a tennis ball, and we have assigned an ID of 1 to the tennis ball, like you can see over here. Uh, so now you can again see that we are able to detect a tennis ball, and I have assigned an ID of 1 to the tennis ball. So now what we have can see that we are able to detect and track the player, and we are also able to detect the tennis ball, and we have assigned the tennis ball an ID of 1. Okay, and the results look quite promising for me as well. Okay, so what we have done for now is that we are able to detect and track the players, and we have also detected a tennis ball as well. And now we will just set over here read from star is equal to true. Okay, so now if I just run this script again, my processing time will be saved. Okay, so let me just show you. So I'm just running this script again, and my output of these frames were not played it, and as for the tennis ball, are being saved in the pickle format. So now the processing time is saved. So now you can see as I run this Python main.py, uh, it doesn't took any time to process. And if I just show you uh, on the output now, so over here you can see that we have this. So if I just show you, so it's currently 10:59 over here, and it's now just modified over here. You can see, and we have the output video, and you can see over here, uh, it doesn't take any time to process, and we have the output video over here. So let's go ahead. So now we'll detect the, so now we will go ahead and detect the tennis court key points. So I will just open the browser for now. Okay, so I will just write over here tennis court key points detection. So I will just go to this GitHub repository, like you can see over here. So we will use this dataset provided in the GitHub repo over here. So you can just open this dataset. So, and you can just download this dataset in your local machine, okay, in the zip format. So we will be detecting the 14 tennis court key points, like you can see over here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So our aim is to detect the 14 tennis court key points. So, and we will be detecting the 14 tennis court key points. In this GitHub repository, they have also provided us with the pre-trained model to detect the tennis court key points, but we will fine-tune the Resonate 50 model to detect the tennis court key points. Okay, and we will be using this data set. Okay, so the dataset consists of 8,841 images. They have used 75% of the images for the training and 25% of the images for the validation purpose. The resolution of image is set to 1280 cross 720, but we will resize the image as well. And plus, what we will do is that they are detecting 14 tennis court key points, and each key point has X and Y position. So there are 28 numbers in total. Okay, so like you can see, we will be detecting this 14 tennis court key points over here. Okay, so you can also use this pre-trained model, but we will fine-tune the ResNet 50 model on this key points data set, and the results look quite good with this data as well. So let me just show you. So here you can see that we have prepared a Google Colab notebook. Here I will just download this data set directly into my Google Colab notebook over here. And then I will just unzip this data set, and here I'm importing all the required libraries over here. We are just creating a torch data set over here. Okay. So now here you can see that we are just standardizing the image into 224 cross 224, and here we are just applying normalization over here as well. And here you can see that we are just reading an image using OpenCV type Python. So OpenCV Python reads the image into BGR format. So we are just converting this image from BGR to RGB format over here. Okay, like we can see, and here you can see that we are just converting the key points into a numpy array and adjusting the X and Y positions. Like I told you that we were detecting 14 tennis court key points, and each key point has an X position and Y position. So we are just adjusting the width and the height of the X and Y coordinates. Like we have resized the image to 224 cross 224. So we are just adjusting the X and Y coordinates accordingly. Okay, so now I will just load the data set using data loader over here. Okay, and then we will just download the ResNet 50 model, pre-trained model over here, and we are just passing. So we are just replacing the last layer with the linear layer, and in the input, I am just passing input features over here. Okay, and in the output, I will get the 14 tennis court key points, and each key point has two positions, X and Y position. So we have 28 numbers in total. So therefore, I have written this 14 cross 2, like we are detecting 14 tennis court key points. So in the output, we have the predictions for the 14 tennis court key points, and each key point has an X and Y number. So we are just moving the model to that device, and here you can see that we are using an abdom optimizer, and I'm using a mean squared error loss, and we are fine-tuning the Resonate 50 model for 50 epochs. You can see that as the iterations and epochs increase, the loss it decreases, and at the end, there is significant decrease in the loss, like very small loss is left. Okay, but if you train the model on 100 epochs, the loss will further decrease and you will have more better results. Then after this, we save the key point model weights in the PTH format as well. Okay, so I will just add those model. I have just added those model weights into this models folder. So in the models folder, we have the tennis ball model weights, and now we also have the key points model weights here as well. Okay, so here 50 means because we have fine-tuned the Retus 50 model for 50 epochs, therefore dash 50.pth. So now we will just create another directory by the name code line detector, and inside this I will just create another .py file by the name code line detector.py. Okay, so first we will import all the required libraries. Okay, we'll import torch and import torch beacon dot transforms as transform, then we'll import CV2 from torch vision. We will import models. Then we will also import numi as np. So we'll just create a class code line detector. Okay, so we will just write init, and the input will be the model path over here. We'll just write self.model models dot resnet 50, and we will use the download a pre-trained model. Okay, and we'll just write over here self.model fc fully connected. So we are going to replace the fully connected layer with the linear layer. Okay, and we'll just write self.model.fc. So the last layer will include the input feature, and in the output we will get the, so we'll just pass the model the input features as the input, and in the output we get the 14 key points, and each key point has the x and y position. Okay, so I will just write torch.load model path, and we have the map location CPU. And we write set.transform transform.compose, and we just write transforms dot to PIL image, and we'll also write transforms dot resize. Okay, and we will just write transforms dot to tensor of like transform dot normalize. We'll just write mean is equal to 0.485, 0.456, 0.406, and we will have standard deviation is equal to 229, 224, and 0.225. Okay, so now we'll just create a predict function over here. So we'll just write image RGB is equal to cv2.cvt color, and we'll just convert the image from DGR to RGB. Okay, and then we have the image tensor. Here we'll pass the RGB image, and we'll just unsqueeze. Okay, we write with torch.no wait, and we write outputs is equal to self.model image insert, and we'll just write key points is equal to outputs dot space dot CPU dot numpy. Okay, and then we'll calculate the original height and original width over here, which is image dot shade 2. Then we'll just calculate the key points. So let's write original width divided by 224.0, and we will just write key points original height 4, and this will return the key. Okay, so now we will plot key points on the image. So we'll just, because our camera is not moving and our camera is fixed, so we will just take the first frame of the video and we'll plot the key points on it, and then we'll loop through all the video frames. So that's like plot key points on the image. So we just write draw key points is equal to self.image dot key points. So just write for I in range, then key points x is equal to int key point I, y is equal to int key points plus 1. Okay, save it will not for text, and we have the input image over here. Okay, our shift simplex, and there we have the scale factor as 0.5 and thickness is equal to 2. And we'll also draw a circle around the key point as well. And we'll write image. We'll pass the x and y position of the key point, and the color of the circle will be red as well, and the circle will be filled. So this will return me the image. So now we'll just plot, or you can say we'll draw key points on the video. So we'll just write draw key points for video. So we'll just write video frames. We'll pass video frames in the input, and we'll also have key points over here. We'll just write output video frame. There will be the empty list, and we'll loop through each of the frames. So we'll just loop in video frames. We'll just write frame is equal to, just call the above function. And we'll just write output video frames dot append frame, and this will return me the output video frames. Okay. So now we'll just call this in the main.py file. So now here we'll just write over here intact tennis score key points over the side for model path is equal to, you just go to the models directory, and here we have key points model weights. Then you'll just call the code line detector. You just, okay, so one thing I just missed is if you want to access the code line detector function outside this directory, you will just go to in, you will just need to create a net.py. Now here you write from dot port line detector import port line detector. Okay, and here I will just write, so okay, so we'll just try port line detector port model path, and here we'll just write code key points is equal to port line detector dot predict, and here we'll just pass the video frames. Okay, so going ahead, we'll draw the key points. So over here, we'll just write draw tennis court key points. So we will just write output video frames is equal to code line detector dot draw key points on video. We'll pass the output video frames and code key points. Okay, so that looks pretty good, and let's run this now and see if it works or not. So now we are just trying to draw tennis court key points. Okay. So one installation video frames. Okay. Court line detector dot rotate. Okay, so we'll just need to pass the first frame of the image video. Let's run this again. I hope this will fix this. So just running this again and I hope this error will be fixed now. So now let's see the output video and see if we are able to detect the tennis court key points or not. So let me just run this now. Okay. So now you can see that we are able to detect the 14 tennis court key points, like you can see over here. Okay, so from 0 to 13, like you can see, we have the 14 tennis court key points, and we are able to detect the 14 tennis court key points, and this is what we want. So uh, now you can see that the results look quite promising, and we are able to detect the tennis court key points. Okay, so this is what we are expecting to detect the tennis court key points, and finally we are able to detect the tennis court key points. Okay. Now we have seen in the output video that a lot of players are being detected, but we only want to detect the two players in the field. So we can use the code key points to detect which player are closest to the court. So let's get started with this. So we only want to detect these two players. So let me just show you the output with the help of output video. So now you can see that lot of players like this, but we only want to detect a player with ID 2 and player 4. So we only want to detect these two players in the field. So we can use these code key points like to determine which player is closest to the tennis court. So in this way, we can detect only these two players which are in the field. So we only want to detect these two players, like player with ID 2 and player with ID 4. We don't want to detect these other players. Okay, so we can use the tennis court key points to determine which player are closest to the tennis court. Okay, so for this, first I will just go to the utils and just create a new .py file by the name dash corning box dash utils .py. Okay, and inside this I will be creating two functions. One is to calculate the center coordinates of the bounding box, and other is to measure a distance between 2 points. Okay, so we can just write get center bounding box, and the input to this will be the bounding box coordinates. So we will just calculate the. So these are the x1 y1 and x2 y2 coordinates of the bounding box. So now we will just calculate the center. What center x? So we'll just write int x1 plus x2 2, and then we'll just calculate the center y. Just write int y1 plus y2 divided by 2. And this will return the center x and center y. Okay, and now we'll just measure the distance. So now measure the distance between 2 points. We can just use this formula. So you can just go to the browser and you can just write measure distance between 2 points. And if you just go over here, we can use this distance formula to measure the distance between 2 points. Okay. So I will just write return. I will just write E10, E20. Okay, and square we have, and then we'll just write P11 minus P21, and here we'll also take a square root. Okay, so that looks good. Okay, that looks quite promising. Okay, so now we'll just go to init.py file, so we can just write over here from .utils import measure distance, and we just want to calculate the center coordinates of the bounding box. So now we will also, what is the error we are starting over here? Now it's fixed. And now we'll just open the player tracker.py file. Okay. So just put this, and inside this we will just create a function choose layers. Okay, and we'll also import from utils with import. Okay, measure distance and get center coordinates of the bounding box. Okay, so let's in the input we will pass. Okay, so we'll just pass the code key points. So we'll just write code key points, and we'll also last the player dictionary. Okay, so we'll just write distances is equal to empty list, right put where ID for bounding box in player dictionary dot items. So we'll just write player center is equal to get center coordinates of the bounding box. Okay, and we will just calculate the minimum distance. Okay, so we'll just write for I in range 0 to length code key points. Okay, because each key point has an x and y position, so we can just write code key points is equal to code key points I and code key points I plus 1. Okay, then we'll just measure the distance, so we just write distance is equal to measure distance, and here we'll just pass the player center, and we'll also call the code key point over here. Okay, and we will write if distance is less than minimum distance, then minimum distance is equal to distance. Okay, and now we'll just write distances dot append track ID minimum distance, and now we'll sort the distances in ascending order. So just write distances dot sort, and key is equal to lambda x, and so we just need to choose the first two tracks. So we just write chosen players is equal to distances 0, 0, distances which are return chosen players. Okay, now we'll just write choose, and we'll just create another function by the name choose and filter layers. And here we have the code key points as input. Okay, so we just write layer detections dash first frame is equal to layer detections. Okay, and we just write chosen layer is equal to set dot choose players, and we'll just pass the code key points, layer detections, and we will pick the first frame. Okay, then we'll just write filtered layer detections is equal to an empty list, and we just write for layer detection in layer detections, and we just write filtered layer dictionary is equal to track ID for track ID for bonic post in layer detection dot items if track ID in chosen player. Okay, and then you just write filtered player detections dot append filtered player dictionary, and this will return filtered player detection. Okay, so it's ready now, and let's go ahead into our win5.py file. So now what we do is we'll just write over here choose and filtered layers. We'll just write player detection is equal to player tracker dot choose and filter players. We'll pass the code key points, and we'll just pass the player directions. Okay, so let's run this main.py file now. So now it's processing. This will take few seconds. Okay, so it's ready now, and let's me just see how my output video looks like. Uh, so now you can see that now we are able to detect only these two players in the field, and we are not detecting these other persons over here, like you can see over here. So now our results look quite good. So in this tutorial, we have created a tennis analysis system where we are detecting and tracking the players and the tennis ball. We are also detecting the tennis court key points. To detect the tennis court key points, we have fine-tuned the RedSnet 50 model on tennis court key points dataset, and we are also applying choose and filter players mechanism to select only the two players in the field by selecting the players that are closest to the tennis court key point. So we are just applying filtering player mechanism to select only the two players in the field by selecting the players that are closest to the court key point. So this is an initial tennis analysis system that we have created in this tutorial. I hope you have learned something from this tutorial. Thank you for watching.